Welcome to the deep dive. We've got quite a stack of sources here today, all pointing towards something really, really fundamental if you want to get your head around quantum computing, quantum linear algebra.
Yeah, absolutely. And these sources, they make it incredibly clear, don't they? Linear algebra isn't just, a tool we happen to use for quantum systems. It is the language. It's how quantum mechanics and so quantum computation actually works.
That's really the core idea right there from the get-go. So our mission today is to take all this material, really dig into it, and pull out, the most important concepts, the foundational ideas, and try to understand the practical side. What does it actually mean to use linear algebra in this completely different quantum way? It's such a shift from classical computing.
A total paradigm shift. And that difference, well, that's where all the potential and maybe some of the hype lives.
Okay, so let's unpack that first bit, this fundamental connection. Why exactly is linear algebra quantum's native tongue?
Well, because the description itself, the very rules of quantum mechanics, they're written in linear algebra. Quantum states, they are vectors. They live in these complex vector space, Hilbert spaces specifically.
Right.
And the operations, the things you do to those states, that we call quantum gates, those are matrices, unitary matrices to be precise. The whole mathematical structure, you need adding states, evolving them, measuring them. It's all linear algebra. It's not like an extra layer we added on top. It's just what it is.
I mean, that's just fundamentally different from classical computers, isn't it? Classically, everything's built on Boolean logic, zeros and ones. We definitely use linear algebra classically.
Oh, all the time. For graphics, data science, machine learning, simulation, loads of things.
But it's a tool, right? We apply it to solve specific problems on top of that basic 0 or 1 foundation. A classical computer doesn't sort of think in vectors and matrices at its most basic level.
Exactly. Whereas a quantum computer, its fundamental building blocks are these linear algebraic objects, state vectors, unitary operators. That's the starting point.
Which kind of hints, doesn't it, that problems that already have a strong linear algebraic structure might be the ones where quantum computers could really shine. That seems like a good place to look for a potential quantum advantage.
That's a very reasonable hypothesis, yeah.
Okay, so if it's the language, how different is this quantum dialect from the, let's say, classical linear algebra maybe more people are familiar with? The sources really hammer home some key distinctions.
Oh, they're fundamental differences. You start with the basic unit of data. Classically, it's the bit. Always 0, always 1. Deterministic. Quantum. It's the qubit. And a qubit can be in a superposition.
Superposition. That amazing thing where it's kind of a blend of 0 and 1 at the same time.
Exactly. It holds this weighted combination of possibilities simultaneously. And that ability comes directly from the math underneath. Classical uses Boolean algebra, simple logic gates. Quantum uses linear algebra, but crucially over complex numbers.
Complex numbers, they pop up everywhere in quantum. Why are they so essential? I mean, why not just real numbers?
Well, complex numbers are absolutely critical. They have that extra dimension, the imaginary part, and that's what allows for phenomena like quantum interference. You get phases, and these phases can interfere constructively or destructively. That's fundamental to how many quantum algorithms actually get their power. Entanglement also relies on it. You just don't get that richness with only real numbers.
And the potential for scaling computation seems completely different too, because of these quantum features.
Hugely different. Classical computing power scales, roughly, linearly with the number of transistors or resources. But quantum computing, because it uses superposition and entanglement, can potentially scale exponentially with the number of qubits.
Exponentially?
Yeah, even a few hundred qubits create a state space, a Hilbert space, with more dimensions than there are atoms in the known universe. That exponential explosion in the available computational space is, well, it's a massive driver of the interest.
But the results you get out are different too. Classical is deterministic, run it again, get the same answer. Quantum, it's probabilistic.
That's right. A quantum computation evolves the state, which contains all these complex numbers called amplitudes for each possible classical outcome. But you don't see that full state directly. When you measure, the superposition collapses, and you get just one specific outcome.
And the chance of getting a particular outcome.
It's determined by the square of the magnitude of its amplitude. That's the Born rule. So you often run the computation many times and build up a probability distribution. It really changes what you mean by solving a problem. You're not always getting the single answer, but maybe statistics about it or an expectation about it.
The sources also flag things like reversibility and the no cloning theorem.
Yeah, also fundamental quantum operations, the gates. must be reversible. Mathematically, they're unitary, which means you can always undo them. Many classical gates like A and D or OR aren't inherently reversible if you lose information. And the no-plumbing theorem, that's a big one. You simply cannot make a perfect copy of an arbitrary unknown quantum state.
You can't just hit Cheryl plus C on a Qubit state.
Nope. Not if you don't know exactly what state it's in beforehand. It has huge implications for how you handle quantum information and design algorithms. You can't just duplicate intermediate results like you might classically.
Okay, let's dive a bit deeper into the actual mathematical grammar then. What are the absolute essential building blocks from these sources we need to grasp?
Right, the core setting, mathematically, is these complex vector spaces, specifically Hilbert spaces. Quantum states just are vectors in these spaces, like arrows with direction and magnitude, but potentially in many, many dimensions and with complex numbers involved.
And these spaces follow certain rules?
Yeah, standard vector space rules, you can add vectors together, superposition, multiply them by scalars, those complex numbers we talked about, which are crucial for interference and entanglement.
Okay, states are vectors. What about the inner product? That term comes up a lot.
The inner product is it's how you relate two vectors. You take two vectors, do this operation, and you get back a single complex number, a scalar. It's incredibly important.
Why? What does it do?
Well, its main job in quantum is calculating probabilities. Remember the Born rule. The inner product of a state with a basis state gives you the probability amplitude. Square its magnitude, you get the probability of measuring that basis state. It also defines the length or norm of a state vector.
And that has to be 1, right?
Exactly. The total probability of measuring something must be 100%, so the vector's norm squared must be 1. The inner product also defines orthogonality, whether two states are completely distinct, like perpendicular vectors.
And to talk about all this, there's that special notation, Dirac notation, brackets.
Ah, yes. Bracket notation. It looks a bit weird at first, maybe, but it's incredibly elegant and concise once you get used to it. A ket, written like is just a column vector representing a quantum state, like 0, 0, or 1 for a single qubit.
And the bra?
The bra-RS is basically the row vector version, specifically the permission conjugate, transpose, and complex conjugate.
Those folded together.
That's a bra. Next to a kate is the inner product, bracket. It gives you that scalar complex number, the projection of state onto state 8, that's your amplitude.
Okay.
And for a standard basis like 0 and 1r, which are orthonormal, the inner product 8 is 1 if I and j are the same, and 0 if they're different. That's the Kronecker delta at that j. Super useful.
What if you put them the other way around? Kate, then bra, case.
Ah, that's the outer product. That combination actually creates a matrix, an operator. A really common one is Tech 8, it's a projection operator. It projects any state onto the direction defined by fix. And generally, linear operators, represented by matrices, are how we describe quantum operations, like gates or Hamiltonians, acting on the state gates.
So going back to a single qubit state, Esh A and COI say plus 6A. That's just a vector in a 2D complex space.
Yeah.
Alpha and beta are complex amplitudes.
And the condition is IO plus beta plus 1. The sum of probabilities is 1, and that linear combination, that is superposition. It's holding both possibilities with complex weights.
Okay, what about multiple qubits? Things get bigger fast, right?
They really do. An n-qubit system lives in a Hilbert space with 2 dimensions. We describe these multi-qubit states using something called the tensor product. It's a way of combining the individual qubit spaces into a larger space. So a 2-qubit state isn't just 2 separate qubits. It's a single vector in a 4-dimensional space.
Representing combinations like 0, 0, 0, 1, or 0, 10, 11 air.
Exactly. A general 2-qubit state is a superposition of all 4 of those basis states, and the quantum gates that act on these n-qubit systems. They're represented by unitary matrices that are 2 by 2 in size. Unitary just means they preserve the total probability. The length of the state vector always stays 1 after the gate acts on it.
And this tensor product structure, it leads directly to entanglement, doesn't it, from a linear algebra perspective?
Yes, entanglement is one of the weirdest, most powerful quantum features, and linear algebra describes it perfectly. Mathematically, an entangled state is simply a state in a multi-qubit system that cannot be written as a simple tensor product of individual qubit states.
So you can't just say qubit 1 is in this state and qubit 2 is in that state.
Exactly. For an entangled state, their fates are linked. The classic example is a Bell state, like 0, 0 plus 11 area. There's no way to factor that into arrows plus 1 arrow times 0 plus d or 1 arrow. They are described only by the combined state. Contrast that with, say, 0, 1 air, which is separable. It's just 0 arrows, tensor 1 air.
And what about density matrices?
Density matrices become really important when you deal with situations that aren't pure states. Like, if you have a probabilistic mixture of different pure states, or, crucially for entanglement, if you want to describe just one part of an entangled system.
So if you have two entangled qubits, you just look at one of them.
Right. Even if the total two-qubit state is pure, like the Bell state, the density matrix describing just one of those qubits will show that it's in a mixed state. It doesn't have a definite state vector on its own. Its description reflects its connection to the other qubit. For a pure state row, the density matrix is simple, process. But for mixed states or subsystems, it's more complex.
And you can measure entanglement using these.
Yes, there are measures like entanglement of formation or concurrence for two qubits, which are calculated from the density matrix. They quantify just how entangled the state is, how inseparable it is. It involves looking at eigenvalues of a related matrix derived from Avro.
Okay, so we've got this mathematical toolkit. Complex vectors and Hilbert spaces, operators, inner products for probability, tensor products for multiple qubits, and this non-separable structure for entanglement. How does all this math actually translate into potentially powerful quantum algorithms?
Right, that's the crucial link. This foundation enables some really interesting algorithms. Probably the most famous early example in quantum linear algebra is the Harel-Hasidim-Lloyd algorithm, or HHL.
HHL, what's its job?
Its purpose is to solve systems of linear equations. You know, the classic problem. Given a matrix A and a vector B, find a vector x such that Ix is B.
Which can be really hard classically, especially if A is huge. Solving AXB can take time that scales polynomially with n the size of the matrix, like NUR or maybe NR, something like that.
Exactly.
Yeah.
HHL theoretically offers an exponential speedup. It can potentially solve for x in time that scales polylogarithmically with n, so like log n to some power. That sounds amazing.
But there's always a but, isn't there?
There usually is. This speedup comes with some serious caveats. First, the matrix A needs to have certain properties. It generally needs to be sparse, meaning mostly zeros. It also needs to have a low condition number, often denoted kappa.
Condition number, what's that, roughly?
It measures how sensitive the solution X is to small changes in A or B. If it's huge, the problem is ill-conditioned, and HHL's runtime scales badly with K, often polynomially. And another big condition. You need to be able to efficiently prepare the input vector B as a quantum state BA.
Okay, sparse, low condition number, efficiently preparable BA. But even then, the output, it's not the classic vector X you get out, is it?
Right.
That's the real catch, right?
That is the absolute key takeaway for HHL. The algorithm doesn't give you the n numbers that make up the vector x directly. It outputs a quantum state, xa, whose amplitudes are proportional to the elements of the solution vector x.
So if you actually need all the numbers in the vector X,
So you have to measure the state xa many, many times to estimate those amplitudes. And getting all n components classically takes about ON measurements, maybe ON log n or something. That completely wipes out the exponential speedup in n.
so HHL isn't really about getting the full classical solution faster in most cases?
Not generally, no. Its potential power comes into play when you don't need the full vector x itself. Maybe you only need to calculate some property of x, like an average value or an inner product XXF or some other matrix M. Or maybe you want to use the state xa as an input to another quantum algorithm.
Okay, so it changes the goal of solving X of B.
Precisely. The steps involved are quite clever. Prepare BA, use quantum phase estimation, a really important subroutine in many quantum algorithms, to find the eigenvalues of A, related to A actually, then do a controlled rotation based on the inverse of those eigenvalues to weight the corresponding eigenvectors, and finally measure an auxiliary quivalent.
Sounds complex. Now, there's a more recent framework the sources mentioned, something called quantum singular value transformation, or QSVT. You said it's maybe more general.
Yes, QSVT is incredibly powerful. It's seen as a unifying framework that captures HHL, Grover search, amplitude amplification, and many other quantum algorithms under one umbrella. It sort of generalizes an earlier technique called quantum signal processing.
Singular value transformation. What's the core idea?
The core idea is to apply a chosen polynomial transformation, let's say dx, directly to the singular values of a matrix A. Remember, singular values are kind of like eigenvalues, but for potentially non-square matrices.
Okay, applying a polynomial to the matrix's singular values. How do you do that quantum mechanically?
It uses a clever technique called block encoding. The idea is you embed your matrix A, which might not even be square or Hermitian, as a subblock within a much larger unitary matrix, let's call it U.
So A is hidden inside this bigger, well-behaved unitary matrix.
Sort of, yeah. When you apply U to a state where certain extra ancilla qubits are set to 0 era, the effect on the main part of your state is like applying A. It gives you a way to access A using unitary operations.
Okay, you've block encoded A into U. Then what?
Then you figure out what function fx you actually want to apply to the singular values of A. Maybe you want to invert them, fx 1x for matrix inversion, or maybe you want to simulate evolution, fx equals era. The next step is to find a polynomial, px, that's a good approximation of your target function, fx, over the range where A's singular values lie.
Like finding a polynomial that looks like 1x.
Exactly. Often, Chebyshev polynomials are used for this approximation. Then, QSVT provides a specific sequence of quantum operations. It involves carefully controlled single qubit rotations, where the rotation angles are derived from the coefficients of your polynomial px. You alternate these rotations with applying the block encoding unitary U and its inverse U.
And the end result of the sequence.
The end result is that you transform the original unitary U into a new unitary, which now block encodes the matrix PA. So you've effectively applied the polynomial function P to your original matrix A, or rather to its singular values.
Wow. So for matrix inversion, you find a polynomial px that mimics 1x, run the QSVT sequence with the angles from px, and you end up with a block encoding of something that approximates A.
That's the essence of it, yes. The amazing thing is the generality. By just changing the target function fx and finding the corresponding polynomial px and its angles, you can use the same QSVT framework to implement all sorts of matrix functions. Matrix inversion, Hamiltonian simulation projecting onto certain eigenspaces, amplitude amplification. It's a really systematic way to construct quantum algorithms for matrix operations. It pushes QLA way beyond just solving X or T.
Okay, so we have these sophisticated algorithms like HHL and this powerful QSVT framework built on that linear algebra foundation. Where might we actually see this stuff making a difference in real-world applications?
Well, quantum machine learning, or QML, is definitely a major area people are looking at. QLA routines seem like a natural fit because so much of classical machine learning is linear algebra, often on very large, high-dimensional data sets.
Right, dealing with huge vectors and matrices.
Exactly. And quantum computers, with their potentially exponential state space, seem well-suited to handle that kind of high dimensionality. So you see proposals for things like quantum support vector machines, where solving linear systems is part of the training, or quantum printable component analysis, which involves diagonalizing matrices.
Basically mapping classical ML linear algebra tasks onto quantum algorithms.
That's a big part of it, yeah. Things like data fitting, regression, solving linear systems that pop up naturally in ML contexts. Some sources even talk about a potential sampling advantage where QLA-based QML might draw useful samples more efficiently.
There's that data loading problem again, isn't there? QRAM.
Ah, yes. The elephant in the room for a lot of QML. Getting massive classical data sets loaded efficiently into a quantum state. This is the QRAM, quantum random access memory problem. If loading n classical data points takes you O(n) classical time, then any O log n quantum processing speedup you might get afterwards is just gone.
The input-output bottleneck, it keeps coming back.
It's absolutely critical. It means either we need breakthroughs in QRAM hardware, which is a huge challenge itself, or we need to focus on problems where the input data is maybe already quantum, or where the classical data loading isn't the dominant cost. Or, very importantly, we focus on hybrid quantum classical approaches.
Hybrid, where quantum and classical computers work together.
Exactly. Maybe the classical computer handles the bulk data processing or optimization loops, and the quantum computer acts as a kind of co-processor or accelerator for specific, tricky linear algebra subroutines that are bottlenecks classically. Many near-term QML algorithms are actually dyes this way.
Makes sense. What about optimization? Another big area.
Yeah, lots of optimization problems either involve linear algebra directly or can be reformulated in ways that use it. Think about algorithms like the variational quantum eigensolver, VQE, or the quantum approximate optimization algorithm, QAOA.
Those are often talked about for near-term quantum computers.
They are. And they typically involve finding the minimum eigenvalue of some operator, Hamiltonian, representing the cost function, or evolving quantum states under such operators. That's all linear algebra. Calculating expectation values, such as is a core step. Adiabatic quantum computing, another approach, solves optimization problems by slowly changing a Hamiltonian again, a linear operator.
And are these also often hybrid?
Yes, VQE and QAOA are prime examples of hybrid algorithms. The quantum computer prepares a state,
measures the expectation value of the cost Hamiltonian, that's the QLA part, and then a classical optimizer takes that result and suggests new parameters for the quantum state preparation circuit. Go back and forth.
So the quantum part is doing this specialized linear algebra bit.
Right. It leverages the quantum properties for that part, while the classical part handles the less quantumly complex optimization loop. It's a practical approach for current hardware. An example like barcode being applied to things like graph problems or engineering simulations framed as optimization.
Any other areas mentioned?
Well, quantum simulation itself is a huge one. Simulating other quantum systems like molecules or materials, that fundamentally involves calculating how states evolve under Hamiltonians, which are linear operators. QSVT is potentially very useful there. Also, solving differential equations, many can be turned into systems of linear equations, so HHL-like approaches might apply, say for Poisson's equation. Network analysis, dealing with graph Laplacians or adjacency matrices, and even financial modeling involving large systems or simulations are other areas people are exploring.
So the potential applications are broad, touching ML, optimization, simulation. But let's get real. The sources are also very clear about the massive challenges. What are the main roadblocks holding back quantum linear algebra right now?
Yeah, it's crucial to balance the excitement with the reality. The biggest, most immediate hurdle is simply the hardware limitations. Qubits are incredibly delicate things, extremely fragile. They suffer from decoherence. They lose their quantum properties very quickly, often in microseconds or even less, just by interacting with their environment. Heat, vibrations, stray fields. It all causes errors.
And just building more qubits isn't easy either.
Not at all. Scaling up the number of qubits while maintaining high quality, low error rates, long coherence times, good connectivity between them is a monumental engineering challenge. We're seeing chips with hundreds of qubits now, which is amazing progress.
But we need way more for the really powerful stuff.
For fault-tolerant quantum computing, the kind needed to run algorithms like Shor's algorithm reliably on large numbers, or potentially complex QLA on huge matrices error-free, we likely need thousands, maybe millions of physical qubits to encode a smaller number of robust logical qubits. We're nowhere near that yet.
And it's not just the number, but the quality and how they're connected.
Exactly. Qubit quality can vary across a chip. And often, a qubit can only directly interact with its nearest neighbors. Limited connectivity restricts the kinds of operations you can do efficiently and makes things like error correction much harder. Plus, many leading qubit types need extreme conditions, like dilution refrigerators near absolute zero temperature.
Adds a lot of complexity and cost.
Definitely. Which leads right into the next big challenge: quantum error correction, or QEC.
Because the qubits are so error-prone, we need a way to fix those errors.
We absolutely do if we want reliable, large-scale computation. And interestingly, QEC itself is heavily based on linear algebra. Codes like the surface code or stabilizer codes use concepts from linear algebra, like parity checks represented by matrices. Error correction procedures often involve projecting the state onto error subspaces to detect and correct flips.
But QEC isn't free, is it? It comes at a cost.
A massive cost in terms of qubit overhead. As I mentioned, you might need thousands of these noisy physical qubits just to create one stable logical qubit that you can compute with reliably. Implementing the QEC protocols themselves involves many extra quantum gates, which adds complexity and can even introduce new errors if they aren't perfect.
So running a QLA algorithm on these error-corrected logical qubits, it adds another layer of complexity.
A huge layer. The QLA algorithm needs to be translated into operations on logical qubits, which then get translated into operations on the underlying physical qubits, including all the QVC steps. The overhead could potentially dwarf the complexity of the original QLA algorithm itself. Making it all work efficiently together is a major research area.
Okay, so hardware errors and QEC overhead are huge. What about challenges within the algorithms themselves?
Right. Even if we had perfect hardware, the algorithms aren't magic bullets. We mentioned HHL's theoretical polylog n speedup, but its actual runtime often has significant polynomial dependencies on other parameters.
Like that condition number and desired precision?
Exactly. For HHL, the cost can scale polynomially, maybe even quite steeply, with 1 and 1. So if your matrix is ill-conditioned, large K, or you need a very precise answer, small I, the quantum advantage might shrink dramatically or disappear entirely, even for large N.
And even if the scaling is better, the actual number of steps might still be enormous.
Yes. The constant factors hidden in the big O notation can be massive. A quantum algorithm might scale better asymptotically, but the sheer number of quantum gates required could mean that for any practical problem size we can currently imagine, A highly optimized classical algorithm running on a supercomputer is still much faster. Finding that crossover point where quantum actually wins is tough.
And we're back to the I/O bottleneck again.
Always lurking. Even with algorithmic speedups, if preparing the initial quantum state BA from classical data is slow, or if you need to extract the full classical solution vector X via measurement at the end, those steps can dominate the runtime and negate any quantum advantage in the processing step.
Finally, the sources mention software and integration issues.
Yeah, the whole ecosystem is still quite immature. Developing quantum programs, debugging them, it's hard. You can't just put print statements everywhere or easily inspect the quantum state mid-computation. The tools are getting better, but there's a long way to go.
And getting quantum computers to work smoothly with classical ones.
That's another hurdle. Quantum computers likely won't be standalone devices, but accelerators working within a larger classical high-performance computing system. Integrating them efficiently, managing data transfer, latency, synchronization, poses significant technical challenges. People are talking about quantum-centric supercomputing architectures, but we're still figuring out how that looks. And of course, there's a big skills gap finding people trained in quantum mechanics, linear algebra, and software development for these machines.
Okay, wow. That's a sobering list of challenges. But people are working hard on them. So looking ahead, where do the sources suggest the field of quantum linear algebra is heading?
Despite the challenges, there's a lot of active research and optimism. On the algorithm front, a big focus is obviously on improving what we have. Can we make HHL less sensitive to the condition number? Can we improve the success probability or reduce the resource requirements for QSVT implementations?
Or find completely new QLA approaches?
Absolutely. Discovering entirely new quantum linear algebra primitives is a key goal. And importantly, given the reality of today's noisy intermediate scale quantum NISQ hardware, there's a huge effort in developing algorithms that are more tailored to these devices.
NISQ-friendly algorithms.
Right. Things like variational algorithms like VQE, heuristic approaches, maybe algorithms that use shallower quantum circuits which are less prone to decoherence. These might not offer the same proven exponential speedups as fault-tolerant algorithms, but they might still provide some quantum advantage for specific problems sooner without needing full error correction.
And it's interesting that QLA research can sometimes boomerang back and inspire classical algorithm improvements.
That's a fascinating side effect. By pushing the boundaries of what's possible quantumly, we sometimes gain new insights that lead to better classical methods. Yu and Tam's work dequantizing certain QML algorithms inspired by HHL and QSVT is a famous example. It led to new, fast classical algorithms that match the promised quantum speedups for those specific problems under certain assumptions. It shows the interplay is complex, and hybrid quantum classical methods remain a very practical path forward for the near term.
And on the hardware side, the push for fault tolerance continues.
That's the long-term grand prize.
Yeah.
Truly fault-tolerant quantum computers. It requires enormous breakthroughs in qubit numbers, qubit quality, connectivity, and efficient, large-scale QEC implementation. It's a marathon, not a sprint.
But maybe steps along the way.
Definitely. Hardware co-design is becoming more important. Designing quantum chips, specifically optimized for certain tasks, like maybe QLA operations or specific error-correcting codes. Exploring entirely new types of qubits, like topological qubits perhaps, that might be inherently more robust is ongoing. And for the NISQ era, researchers are developing clever error mitigation techniques, ways to reduce the impact of noise even without full QEC, things like circuit knitting or decomposition to run larger problems on smaller devices.
So the ultimate aim is still to find those problems where quantum linear algebra gives a real demonstrable advantage.
Yes, finding the killer applications. And demonstrating advantage means rigorous benchmarking against the absolute best classical algorithms running on the best classical hardware for that specific problem instance. It's not enough to just compare against a naive classical method.
And those applications are likely to be specific niches initially.
Most likely. Problems where maybe the input data is naturally quantum, like in simulating quantum systems, or where you only need a specific property of the output vector, like an expectation value, thus avoiding the worst of the I/O bottlenecks. Those seem like the most promising candidates for near-term advantage.
It really sounds like achieving that advantage is a complex equation. It depends on the problem size n, yes, but also the matrix properties like sparsity and condition number A, precision A you need, the specific capabilities of the quantum hardware, qubit count, error rates, connectivity, how efficiently you can do state preparation and measurement, and how good the classical alternatives are.
It's an incredibly intricate interplay of all those factors. Progress is likely to be incremental, We'll probably see advantage demonstrated for very specific, carefully chosen problems first, rather than a sudden, universal speed up for all linear algebra tasks.
Okay, so let's try to wrap this up. We've seen that quantum linear algebra isn't just math for quantum computing. It is the fundamental language based on complex vectors, operators, tensor products. It's inherently different from classical linear algebra.
And that difference enables potentially powerful algorithms like HHL, and especially the unifying framework of QSVT. These hold promise for impacting fields like quantum machine learning, optimization, and simulation, where linear algebra is key.
But we've also got to keep our feet on the ground. The challenges are significant. Fragile hardware, the massive overhead and complexity of quantum error correction, algorithmic performance depending heavily on problem details like condition numbers, the persistent data input-output bottleneck, and the need for better software tools and integration.
The path forward really depends on progress across all these fronts. Simultaneously, better theory, better algorithms, including NISQ-friendly and hybrid ones, and of course, much better hardware, eventually aiming for fault tolerance.
It's definitely a complex and fascinating journey ahead for QLA.
No doubt about it.
So here's something to think about for you listening. Considering everything we've discussed today, the reality of noisy, limited qubits, the huge cost of error correction, how algorithm speed really depends on specifics like matrix condition numbers, and that stubborn problem of getting data in and out efficiently, what specific characteristics would a real-world linear algebra problem need to possess right now or in the very near future for a quantum computer to offer a genuine, practical, demonstrable advantage over the very best classical supercomputer algorithm we have for it? It's clearly not just about that theoretical log n speed up anymore. It's about navigating this incredibly complex reality of actually making it work. What does that ideal first problem look like?